Another example is in an MRI machine. Uh, so, so what happens in an MRI machine is that the patient is subjected to very, very strong fluctuating magnetic fields. I mean, the physics of MRIs is just very fascinating, but that would take half of a lecture to discuss that. Um, but essentially, the patient is subjected to very strong, rapidly fluctuating magnetic fields, right? All right. Now, sometimes a patient has to be sedated when they're put inside the MRI machine, and particularly if it's children, like children might have a hard time staying still for 45 minutes to an hour. So sometimes they're sedated when they're put inside the MRI machine. But still, you want to be able to monitor the patient's vital signs while they're in there. And so you have this device attached to the person's pulse, I mean, to the person's finger, which can monitor their vital signs like their pulse rate and all that stuff. Okay, and that is and the cable. So that device is connected to a cable that goes outside. Now, when you're placing that cable, um, suppose you're not very careful, and a part of the cable is touching the patient's arm like this, like in this figure, right? Okay, and so you put the patient inside the MRI machine, turn the machine on, right? And now what's happening is a magnetic field, a rapidly fluctuating magnetic field is acting on the patient, but notice that there is a loop that you have created. Part of the loop is the patient's arm, and the other part is this wire. That makes sense? So now you have a fluctuating magnetic field over a loop of which a patient's arm is a part of. So what do you think will happen over there? There will be induced EMF over that loop, right? The red loop that you can see. And that will drive a current through this red loop, which means a current will pass through the patient's arm, right? And what will that do? What's the effect of that?
It will create eddy currents.
No, I mean, that is an eddy current. That's an example of an eddy current. But what is the effect on the patient? So there is a current passing through part of their arm. So what does that do? The answer is third-degree burns. So this has actually happened before, and people had to learn not to do this the very hard way from when burns started happening in MRI machines. And so nowadays, MRI technicians are trained to make sure that there is no loops in the way their cables are placed. That clear to all of you? All right. Another interesting application is in an electric guitar. So in an ordinary guitar, you have that. I can never remember like like this part of the guitar. That's my drawing of a guitar. So this part. So that is basically like a sound box, right? So you have air over there, and so when you play the strings of the guitar, the air in the wide part of the guitar starts fluctuate. The sound waves are amplified by that. You don't have this in an electric guitar. So the amplification of the sound is done entirely electrically. But how is the sound converted into an electrical signal in the electric guitar? Well, just above the strings, you have you have a solenoid, right? Just above the strings, you've got this solenoid. And so you can see the solenoid over here. A solenoid is also called a coil. So solenoid and coil mean exactly the same thing. So you have this solenoid, small solenoid, just above the strings of the guitar, and you have a magnet inside the solenoid, a permanent magnet, which temporarily magnetizes this part of the guitar string. So this part of the guitar string acts like a little magnet because it's sitting in front of a permanent magnet. We've seen in chapter 28 that when you put iron in a magnetic field, it gets magnetized. So the part of the guitar string just above the solenoid acts like a little magnet. And so when the guitar is played, this goes up and down, right, in a particular way. And the magnetic field over of this string acts on the solenoid, right? So there is a induced electric field inside the solenoid and EMF in the solenoid, and that EMF drives the current through the solenoid. And that current will have the same pattern as the sound, as the vibration of the string. And so you can so you're converting that vibration into an into a fluctuating electric current, which you can feed to an amplifier. And so that's how the amplification happens in an electric guitar. That makes sense? All right. There's many other applications too. So in a credit card, there is a magnetic region over here. And in the old days, now this is kind of ended now, but in the old days, you would swipe this credit card. So that means you would pass that magnetic region through this narrow groove, and that would be swiping the credit card, right? So how did the swipe work? Well, this magnetic region in the solenoid is actually made up of magnetic particles, which made up of nanoparticles, which are like tiny little magnets. And so some of those nanoparticles could be pointed this way, some of them could be aligned this way, some of them aligned this way. So either one way or the other. So there could be a region of where all the nanoparticles are lined up like this, then the next region they're lined up like this, next region they're lined up like this, and so on. Now, if they're lined up pointing up, that could be a 1. And if they're lined up pointing 0, that could be down, that could be a 0. So you can encode information, any information you want, in binary form that way, right? So 1 would be the particles lined up one way, and 0 would be the particles lined up the other way. And if you can do a 1 and a 0, that means you can, in binary, that's binary. So you can encode any information you want in binary that way. And so that is how information about you and your credit card is encoded in that magnetic strip, right? And so how do you read that magnetic strip? All you have to do is just put a little solenoid over here. And as the magnetic strip is being passed over this solenoid, the magnetic fields due to these nanoparticles will keep on fluctuating depending on how the particles are arranged, and that would create a fluctuating magnetic field. A fluctuating magnetic field produces an electric field, and that electric field will drive a current through this solenoid in exactly the same pattern. That makes sense? And that's how you can read how the nanoparticles are arranged in the magnetic strip. And old hard disks worked exactly the same way. So the information was encoded on the hard disk with these nanoparticles. And the reader of the hard disk just consists of a solenoid. So as the disk spins, the nanoparticles will produce a fluctuating magnetic field over the solenoid in the disk reader, and that would induce an electric field and a current inside the disk reader. And so that's how the computer would be able to read the disk. That clear to all of you? All right. Okay, so there's many other applications as well. So this is an exercise bike, which we talked about earlier. Let me just show you this video if it works. All right, so you have this highly fluctuating current in these loops. And so the current is very large and fluctuating very rapidly. And so you have strong electric fields in the region in between in these loops. And so when you put a conductor in those regions, the eddy currents are so strong that they cause the conductor to become red hot. That clear to all of you? So that's an example of eddy currents. I'll show you another example. So some of these links are demonstrations that I have done in class. So in this demonstration, I have this region of magnetic field. So you can see that the two poles of the magnet, those are the vertical bars, and then I'm going to swing some pendulums through these regions. So let's see. Let me see if I can have you hear the sound. Region. And I have a bunch of pendulums. Can you hear the sound? Over here, made of various materials. This one is made up of plastic. So I'm just going to swing it. Right. So in case you can't hear, that's a plastic pendulum. So you're not going to have any eddy currents over there because it's a non-conductor. Swinging for a while. Okay. Now I'm going to use aluminium. So I have two materials here, aluminium and copper. Neither of them are magnetic. So if I just hold a magnet to either of them,
Yeah, see, the aluminum is not magnetic at all, but it's a
what would
conductor
happen
at
if I
least.
swing this piece of aluminum, this aluminum pendulum, through the magnetic field? So let's see what happens.
Do you see how quickly it stopped?
Notice that it came to a stop rather abruptly, right?
So the reason that it stops so abruptly, and you can watch the video on your own, the reason that it stops so abruptly is because of eddy current braking. So the conductor is passing through a strong magnetic field, and as we saw earlier, that causes eddy currents, and that's an example of eddy current braking. So there's many applications of this. Okay, so please watch these other videos as well. All right, I'll talk about one more amazing application. So Jupiter has 4 moons, right? Those are, I mean, it actually, how many moons does Jupiter have in total? Does anybody know that? How many moons does Jupiter have? The answer is 67. But so Jupiter has 67 moons, but the 4 largest ones are, which are fairly close to it, are called the Galilean moons because they were first seen by Galileo with the first telescope that he ever invented. However, so have you guys ever seen Jupiter through a telescope? If you ever go to if they at the Dyer Observatory at Vanderbilt, they have these viewing nights. I would highly recommend going to one of those. And sometimes they have their telescope set up and you can look at Jupiter. It's just amazing sight to see. And you can also see the Galilean moons next to Jupiter. So anyway, so one of these Galilean moons is named Io. And when the Voyager spacecraft, I think in the 1970s, first flew past Io and took pictures of the surface of Io, scientists were completely stunned because it had this yellowish appearance. And the most amazing thing about Io was that there were these volcanoes going off right in real time. You could see volcanoes actually going off in real time. The surface of Io is full of volcanoes, active volcanoes, and these volcanoes are putting out, and those are nothing like the volcanoes on Earth. So they shoot out material which goes straight into space. And so it's very powerful volcanoes. And here you can see these volcanic plumes, which can be seen from space. So huge volcanic plumes. And so the question is, where does Io get so much energy from? And since this volcanic material just covers the surface of Io, that's why it has this yellowish appearance because of all the sulfur that comes out from the volcanoes. Anyway, but where does Io get all this energy for these volcanic eruptions? There are two explanations for this. Actually, both of them are true. Both of them are valid. But one of them is a little more important than the other one. And the more important explanation is called tidal flexing, which we don't have time to get into. But the second has to do with eddy currents. So Jupiter has an extremely powerful magnetic field. My Microsoft Word is dead. Okay, so Jupiter has an extremely powerful magnetic field, much stronger than the Earth's magnetic field, way stronger than the Earth's magnetic field. And Io has a lot of iron in its mantle and core and surface. And so as Io is passing through the tremendously powerful magnetic field of Jupiter, that induces crazy eddy currents inside the surface of Io. And as a result of that, a lot of heat is generated, which shows up in the form of volcanoes. That makes sense? So that is one of the reasons why Io gets its energy, and the other has to do with gravitational tidal flexing, which we don't have time to get into. But the eddy currents is one of the reasons why you have these crazy volcanoes on the surface of Io. In fact, Io is the only other place in the solar system that's known that has active volcanoes. No other, every other place has dead volcanoes.